So I've said that separations use solubility to help isolate compounds, so we need to remember a few things about our solubility rules. Like dissolves like, for instance. That means that our nonpolar compounds, our nonpolar organic compounds, are going to be more soluble in nonpolar solvents. Likewise, our polar compounds will be more soluble in polar solvents. So an example from your lab book is that salts are easily removed after a reaction, an organic reaction that we've done. We'll see plenty of salts being made, and in fact, we discussed that when we discussed our counter ion section of chapter 3. But we can easily remove these salts by washing your reaction solution with water. We know salts will easily dissolve in water since they're ionic compounds. Some organic compounds are very polar, so that means that they have some solubility in water. Extraction of these very polar organic solvents into your non-polar organic layer can be very difficult, so we may want to use the salting out process. The salting out process uses a sodium chloride solution, okay, which we often refer to as a brine solution in organic chemistry. You use a brine solution to decrease the organic compound's solubility in your aqueous salty solution. So basically, instead of just using water as your aqueous solvent, you use a brine solution which decreases the very polar organic compound solubility in that aqueous solution. Your organics should then preferentially dissolve in your nonpolar solvent, and you would be able to separate out your compounds. Extraction can be very efficient if one of your compounds is able to be converted into an ionic form, if you have multiple compounds you're trying to separate out. Ionic compounds, as I mentioned on the last slide, are soluble in the aqueous layer. Your non-ionic compounds would stay in the organic layer, like traditional organic compounds do. The separation of the two layers would, of course, separate out the ionic compounds from the non-ionic compounds. Ionic forms of organic compounds can be produced through acid-base reactions, which we've just finished looking at from our chapter 3. Sodium hydroxide, or a weaker base, can be used to deprotonate compounds. Hydrochloric acid, likewise, can be used to protonate to form ionic versions of these organic compounds. The acid-base equilibrium dictates how much of an ionic form is produced. So here we see figure 6 from your lab book, and we see examples of acid-base reactions. So in the top example, we see a carboxylic acid being deprotonated by either your hydroxide anion from sodium hydroxide or your carbonate, your bicarbonate anion from your sodium bicarbonate. We see that that reaction is successful, and we create the carboxylate anion that would preferentially go into the aqueous layer in a wash. We see yet another example of that in the middle reaction. This time only hydroxide anion is a strong enough base to cause the deprotonation to happen in a substantial way. At the bottom we see an amine. We know amines are bases, so they can react with acids like we see here in H3O+, if we had added hydrochloric acid to some water. And we see that with the introduction of an acid to an amine, we can create an ammonium cation situation that, of course, is an ionic form and would be preferentially solubilized in the aqueous layer as opposed to the organic layer. We know that the acid-base equilibrium dictates how much ionic form is produced of our formerly only organic products. So once again, I've put up the pKa formula here. Your lab book does provide you with pKa's, but at this point, we should be able to qualitatively assess the reactions we're going to look at on this slide. So this is figure 7 from your book, showing our specific molecules that we're dealing with today, or at least some of them, and the acid or the base reactions that they will undergo. I don't like how they've organized this, so I've kind of rearranged it. Now we are comparing our two compounds that can react with base, p-toluic acid and p-tert-butylphenol, and what happens when we introduce our sodium bicarbonate to our solution that contains both of these compounds. What we see is that p-toluic acid will react with the bicarbonate anion and become deprotonated, and p-tert-butylphenol does not react with the bicarbonate anion. We can tell from the pKa values that they've got assigned, as well as from a qualitative assessment, that equilibrium in that top reaction should favor the products. So we should have plenty of the p-toluate anion being formed, which would of course preferentially go into the aqueous layer. Since our p-tert-butylphenol doesn't react with sodium bicarbonate, we see it staying in its organic form and remaining in the organic layer. Down below, we see the p-toluic acid and p-tert-butylphenol reactions with sodium hydroxide. Notice both of those molecules will become deprotonated in the presence of sodium hydroxide, and in fact, both reactions favor the production of the ionic form of those compounds, the anion form, the carboxylate, and the oxide. So if we were to use sodium hydroxide as our first wash, we would actually be isolating both the p-toluate anion and the p-tert-butylphenoxide anion in the aqueous layer. That's not suitable for our purposes. We're trying to separate out all three of our different compounds. So logically, it makes sense for us to use our sodium bicarbonate as the first wash to selectively isolate the p-toluate anion, and follow up with a second wash of sodium hydroxide. The p-toluic acid should no longer be present, and so a hydroxide wash will, or a hydroxide extraction will only remove your p-tert-butylphenol. So again, because we are purposefully trying to pull out a desired compound, both the sodium bicarbonate and the sodium hydroxide introductions would be considered extractions. So hopefully going through those equations helps explain why we need to wash with two different bases. We can see this similar thing in acid-base equilibrium being used to take advantage of washing with perhaps two different acids. Traditionally, it's more different bases that get used as opposed to different acids in extractions and washings. So the things to remember: extractions and washing take advantage of solubility rules and acid-base reactions to isolate these compounds. We can use this knowledge to our advantage. And once the ionic forms are isolated, we can go back. Acid-base reactions are in equilibrium, so we can force the reaction, force the equilibrium back towards the organic form of those molecules to reprotonate or deprotonate our molecules back into their original organic forms. Typically, when we do this, and in our case this week, we will have two anions that we will be reprotonating with acid in a later step. We see that this typically gives precipitates because your compounds, your anions, are losing their solubility in the aqueous layer, and your solids can be filtered and isolated carefully. Sometimes we will instead isolate oils or liquids. This is typically more from the organic layers where we're perhaps getting a small amount of oil or a liquid, and you can crystallize those out and yield a product solvent, a solid product. Remember, if you are trying to crystallize and you have something like an oil that doesn't seem like it wants to crystallize, you can always scratch the surface with a glass stirring rod. The final figure for this lab is figure 8. It's basically a flow chart of what we're doing and what should be in each layer. So you can refer back to this throughout the lab. They are using some condensed formulas for our molecules, so you kind of need to look up at the top as a key. You can always annotate and describe what you think, which molecule is which. And in fact, this is kind of an interesting illustration of how they've used condensed formulas to illustrate benzene rings. I have once again shown us what our structures are. At the bottom, we see acetanilide, which we had not looked at before, although you should be familiar with the acetanilide structure from other labs. We see the molecule on the upper left is our p-toluic acid, and the molecule on the upper right is our p-tert-butylphenol. So hopefully looking at these structures will help further explain what's going on with the acid-base chemistry that we're using to separate out these molecules by extraction and washing.